Welcome everybody to Chemistry Mnemonics. Mnemonic device is of course something that helps us remember. So I have about, 30, 35 of these, and I should be able to get them in within the 15 minutes. Let's start. These are roughly in order of the course. Energy. Remember, I always pay honor to our great friend and colleague, Mr. Weiss, who brought this to my attention. The Weiss tower of phase, if you draw an up arrow and a down arrow, the up arrow next to SL and G, this is the phase change. So if I'm going in the direction of S to L or L to G or S to G, well, energy and entropy, that's an up arrow for both. They're both increasing. However, if I'm going in the opposite direction, a down arrow, gas to liquid, liquid to solid, gas to solid, well, energy and entropy are both decreasing together. A very, very useful tool and tip. Nuclear, there's really just one that came to mind. Very, very popular one, fission division. That's going to remind you that if you're choosing, fission means that you're going from a larger nucleus to two smaller nuclei, kind of like binary fission in biology. You're splitting it. It's called splitting the atom into smaller nuclei. Next, periodic table and bonding. This is where we really have the lion's share, the big amount of mnemonic devices. For example, we say that metals are big losers. Why? They're big atoms and they're losers of electrons. Next, if you're ever asked which of the following element is diatomic, well, remember the name of Brinkelhoff. Br2, I2, N2, Cl2, H2, O2, and F2. These are the 7 diatomic elements. Next, I don't know if this is so useful. Sometimes I'm asked, well, how do I know what a polar bond is? Well, I'd say a way to remember that there are two different nonmetals in a polar bond is to think of N and S on the periodic table. Notice they're touching each other in the same way that a bond would form between these two different nonmetals. And you can also think of it this way. Why did I choose N and S? Because N is like the North Pole and S is like the South Pole. And of course, these are the two poles opposite. They're different poles, just as these are different nonmetal elements. Maybe that helps. Our favorite guys, SNAP. Remember, S stands for symmetrical molecule, N stands for nonpolar molecule, A stands for asymmetrical molecule, and P stands for polar molecule. Of course, our favorite molecule of all, water, we look at it and we say, oh, snap. When I try to draw two mirror images, I fail. I only get a mirror image across this axis, but I don't get a mirror image across this one, so I would call this asymmetrical, and therefore it is a polar molecule, whereas if I have one like CH4, notice that the H's are symmetrically arranged, what we call a symmetrical distribution of charge, therefore it is considered a nonpolar molecule. Next, barf. This helps clear up a misconception. Remember, guys, B stands for break and A stands for absorb. So if I want to break the bond between these two chlorines, the Cl2 has to absorb enough energy to split them into two different atoms. The reverse, if I want to form a bond between two chlorine atoms, it's going to have to release energy in the process. So barf is a great way of keeping these two things straight. Also, TICS, I have Mr. Russo to thank for this one, certainly. Transferring electrons happens in an ionic bond. Ionic bonds, of course, between metals and nonmetals, so once you recognize it's ionic, this will help you remember that you're transferring electrons. If you're dealing with a covalent bond, which is nonmetal-nonmetal, then this is going to remind you that they are, of course, shared. Say hi on the phone. Well, this is going to remind you the three molecules, or I guess more specifically, the three bonds that, when found in molecules, are the really, really strong intermolecular forces called hydrogen bonding. Hi on the phone, the hi is the hydrogen, and the phone is the fluorine, the oxygen, and the nitrogen. So you're going to remember that HF, H2O, and NH3 are the three molecules that have hydrogen bonding. Say hi on the phone, and they're also listed in order of decreasing intermolecular force strength. Next we have, I heard this one from Mr. Russo. This is going to remind you the number of bonds that these 4 key elements are going to form. in order to be satisfied. Hydrogen is going to form forms one bond. Each oxygen has to form 2 bonds. Nitrogen has to form 3 bonds, and carbon has to form 4 bonds. You can also think of it this way. Hydrogen has 1 unpaired electron. Oxygen has, if you remember, 2 unpaired electrons. Nitrogen has 3 unpaired electrons, and carbon has 1, 2, 3, 4 unpaired electrons. Honk honk. Now what I did is I extended the idea to this. If I have these, if I had 3 diatomic molecules. Now C2 doesn't actually exist, but I'll leave it in there anyway. If you have H2, you're going to notice that molecule has to have a single bond. O2 has to have a double bond. N2 has to have a triple bond. And although it doesn't exist, if it could exist, carbon would be the only one that could have a quadruple bond. But of course, we don't actually consider it as something that could exist. I guess I have to sing this one first. Oh, no, no, slow. Oh, no, no, slow. Molecules go. Oh, no, no, slow. Well, this little song is meant to remind you about the properties of molecules. Well, first of all, the CO stands for covalent bonds. The NO stands for non-conductive. The LO stands for low melting point and boiling point, which is generally true, particularly for smaller molecules. And how do molecules go? Well, molecules go slow, meaning they react slowly. There are a lot of bonds to break. So if you had the choice between free ions and molecules, you're always going to say the free ions react fast, but the molecules react slow. When valence is 8, an atom feels great. Well, this will remind you that atoms are really very miserable people. They do not have what they want. This only has 7 valence electrons. Remember, it's only going to feel great once it has 2, 4, 6, 8 valence electrons like this fellow over here. Remember, an ion is always happy because ions always have 8. There are a couple of exceptions, but that's a great rule. In formulas and equations, well, I just really have this one, swap, drop, and reduce, and I kind of make it into something musical. We swap, we drop, and we reduce. We reduce, we reduce, we swap and drop, and we reduce. Don't we, class? And what does this mean? Well, when we swap, we take the oxidation states and we exchange them, and then we take those that we've exchanged and we drop them, like so. Can I reduce a 3-to-2 ratio? No, I can't, so that's my final answer. Swap, drop, and reduce. We're now on to the gas laws. Remember, on a little piece of paper, you can write PTV. We folded hot dog style, of course. And if you notice, when I rotate the page so that the temperature remains constant, pressure has to decrease, but volume increases when temperature is constant. Remember, this is called an indirect relationship. So this is one use of the PTV. That's our one and only indirect relationship in the gas laws. A shout out to Mr. Cisak, who came up with this. He said, well, it's kind of like in the summertime, you feel very low pressure on you, and you're at the beach and very, very high temperatures, and you're thinking, my God, this is ideal. Remember, these are conditions for ideal gases. Of course, I just added this. You imagine someone with the pretentious wraparound sunglasses and the pretentious crew cut, and of course reading the latest installment of Vampire Diaries. Oh yes, this is ideal. Let's move on to solutions. Well, students often have trouble remembering what side is positive on the hydrogen atom. Well, we all know that the water molecule looks like Mickey Mouse. And well, if we think of it this way, if we have someone named Saint Mickey, that the sign of the saint looks like a positive sign, that means there's a negative sign on the other side. It's a helpful little tool. And remember, this helps you in such a question if I asked you to draw water molecules around a, let's say, negatively charged ion. Clearly, you're going to have the positive hydrogens facing the negative side. Let's start off with the bad joke. Question, why did the guy jump into the homogeneous mixture? Because he wanted to be part of the solution. Get it? My terrible way of remembering that a solution is the same thing as a homogeneous mixture. A much better joke. What kind of bears dissolve in water? Polar bears. It's going to remind you that since water's polar, anything that will dissolve in it will also be polar. That is, specifically, what kind of molecules will dissolve in water. On to kinetics. I had a colleague at my previous district who said that the potential energy diagram kind of resembled or suggested to him a tombstone. And as we know, in the English-speaking world, there are 3 letters, RIP, on the tombstone. That will remind you that the first part is the reactants, the middle portion are the intermediates, and the third portion are the products. For equilibrium, I just have a statement, equal rates, constant concentrations. But I also like to add a little dance to it. Can you hear this? So as we're doing that, we say the words equal rates, constant concentration. I can help you. We're into redox, and we have a bunch of things to say. One is a little thing that I came up with. The oxidizing agent is the thing that gets reduced. It's rhythmic, and it can help you remember this. But why don't we set this to music? The oxidizing agent is the thing that gets reduced. The oxidizing agent is the thing that gets reduced. The oxidizing agent is the thing that gets reduced. Hope you like that. This is classic, of course, guys. An ox, red cat. The anode is oxidation's location. The cathode is reduction's location. Of course, as reduction occurs, the cat gets fat. The cathode gets bigger. As the anode, as oxidation happens at the anode is going to get skinny because, remember, in oxidation, the metal, generally speaking, is turning into these free ions which enter solution. So the solid gets smaller and the ions get more numerous. Then we have oil rig. Oxidation is losing electrons. Reduction is gaining electrons. You might also like to call it oily because oxidation is losing electrons. Another one, I like it, most people don't. Leo says grrr, Leo the lion. Losing electrons, oxidation. Gaining electrons, reduction. I like that one. A shout out to Mr. Wise for the last one on this page. If you split the word redox into red and ox, you're going to see that red is on the left side. And this will remind you that, oh yeah, electrons have to go on the left side of a reduction reaction. So here is the reduction here. So we have 2 electrons there on the left side. But if we're dealing with oxidation, electrons have to go on the right side. Here's the right side. I need 2 electrons there. Thank you, Mr. Weiss. Organic chemistry, well, I have the statement, saturated substitution. Saturated substitution. It's very rhythmic. It's going to remind you that substitution only can happen if you have a saturated hydrocarbon. Of course, what happens in substitution? These are all single bonds. The fluorine is going to come over and substitute itself in for hydrogen. Voila! I guess we could also call it swapstitution. Or not. Next is SSS. S is for single bonds. S is for saturated hydrocarbons. S is for substitution. Oh, how sad. Look, I have 3 unhappy carbons. Why are they unhappy? Because it's 1, 2, 3, 4 happy carbon. Each carbon has to have a total of 4 bonds. Let's do it. 1, 2, 3, 4, and look, happy carbon. And 1, 2, 3, 4, happy carbon. And 1, 2, 3, 4, happy carbon. Atomic structure, guys. Remember, another term for an electron orbital is an orbital cloud. And remember, when you have an orbital cloud, guys, there's a chance of electrons today. And just enough time, guys. Remember, electric abs, that will remind you that the abs are acid-base salts, and they are the electrolytes. And finally, Mr. Russo reminded me today of bad. What's bad? B is for base, A is for accept, A is for acid, D is for donate. Of course, you're accepting. H plus, a proton, you're donating proton. Bad. Okay, hope that helped. I've been studying.